Okay, and then let's recap what those estimates worked out to be. So our estimate of beta 1 worked out to be this guy, right, where the correlation times the ratio of the standard deviations, and our beta naught hat satisfied this, beta y bar minus beta 1 hat x bar. So and then remember, we've already stated those things in the previous slide. Okay, so that's a bit of a recap. So this helps us interpret some of these quantities, because I think part of the key of linear models and linear regression is that the coefficients are very interpretable. So take beta naught as an example. What is beta naught interpreted as? It's the expected response when the predictor happens to be 0. So I would write that like this: the expected y given x equals 0. And of course that's, you know, our expected y given any value of x is beta naught plus beta 1x. So of course if we plug in x equals 0, we get beta naught. So the interpretation of beta naught is the expected beta, or the expected response when the regressor is 0. But no, this isn't always of interest. So if x equal to 0 is impossible, or it's way far outside the range of the data, in our height example, that was of course the case, right? No one as an adult is of height 0, right? You know, or even no one is ever of height 0. So it doesn't make any sense to interpret the intercept then. So there's a trick so that you can get the intercept to be interpretable but not tinker around with the slopes. So here's our model, y equal beta naught plus beta 1 xi plus epsilon I. Let's imagine if I shifted xi by amount a, right, and then I subtracted a beta 1a right there, and then I have to add a beta 1a right there, then I wind up with the same exact model, right? Beta 1 times the shifted x, right? So the slope hasn't changed, but the intercept has changed. So now the intercept is the intercept you would interpret when this new variable xi minus a is 0, or in other words, when xi actually takes on the value a. So if you take your regressors and shift them by value a, then that simply changes the interpretation of the intercept, but it won't change your slope. And often what you do is you set a to be the average of the x's, so the intercept is interpreted as the expected response at the average x value in your data. And so that's how you can often shift your data so that your intercept actually has meaning. Okay, let's talk about interpreting the slope now. So imagine if we took the expected value y given x took the specific value x plus 1 minus the expected value y given x took the specific value x, right? So that would be beta naught plus beta 1 times x plus 1 minus beta naught plus beta 1x. Do the arithmetic out, that's beta 1. So if we look and read and interpret this guy correctly, that is that beta 1 is the expected change in the response per 1 unit change in the predictor. Okay? So let's talk about, we talked about what shifting x does. Shifting x doesn't change the slope, it only changes the intercept, of course. And so what happens if we do some sort of unit change of the x by some multiplication? So we have yi equals beta naught plus beta 1 xi plus error, okay? And then we multiply and divide by an a, then we wind up with the same regression model, but now x times a as the predictor and beta 1 tilde as our slope, where beta 1 tilde is beta 1 divided by a. Okay, and so this is pretty easy. So multiplication of x by a factor of a results in dividing the coefficient by a factor of a. So it's a little bit easy to get messed up in these calculations. So, but if you keep track of the units, then it's easy. So as an example, if x is height in meters and y is weight in kilograms, then beta 1, which is a slope, has to be in units of y per unit of x, so kilograms per meter. Converting x to centimeters implies multiplying x by 100, right? And then to get beta 1 in the right units, we have to divide it by 100, okay? And so here's the unit discussion right here. We have x meters times 100 centimeters in 1 meter winds up with 100x centimeters. And beta 1, which is in kilograms per meter, times 1 meter in 100 centimeters works out to be beta 1 over 100 in kilograms per centimeter. So if you keep track of your units, you can't mess it up. So we could use our regression equation for prediction at a particular value of x. All we have to do, our predictive value of x, let's just say y hat is equal to beta naught hat plus beta 1 hat times x. Just plug in that value of x. So I don't know, we should call it maybe y hat of x. Notice at the particular observed value of x is we automatically get these y hat i's if we plug in the observed x i's. And it is in fact the difference between the y hat i's and the y i's, the sum of the squared distances, where the y hat i's live in the space governed by that regression line, is what we're trying to minimize.